The advancer. Okay, I have some notes. I'd like to thank the organizers for the opportunity to be here today and speak. I'd particularly like to thank Al for being such a inspiration over all of these years and really a guiding light for the community. I'm, like Martin and Min earlier, a representative from outside of the immediate group of students that you have advised and faculty you've worked with. And I can just say that the impact goes far beyond MIT, circles the globe, and it's just so great to be here with you today. So happy birthday. I also would like to say that we talked last night about Al being nervous before lectures, and I am extremely nervous today. Okay, so you need to work with me. Martin Vetterly's in the house. This is a problem. There are just so many pioneers and experts here that this has just been extremely difficult to try to think of what to speak about today. So I hope you'll work with me as we go through this. So as my title indicates, we're going to talk about cycles a little bit today. Signal processing was born in an era of in a golden age of physics. And we're now entering or have entered a golden age of data. And really the future of signal processing depends on how we navigate these waves or windsurf through these waves, if you will. And in order to look at the future, I think or think about the future, it's really important to look at the past. So let's go back to a time period, I believe around when Al started at MIT, about 1500 BC. And let's talk about Babylon. So how many people know ancient history of mathematics? It's very, very illustrative in thinking of these cycles. So the Babylonians were absolutely obsessed with data, okay, and calculating, and they were unbelievably accurate at calculating, right? Calculating astronomical events, for example. They were so obsessed with data that the way that they taught students, we talked about education last night, the way they taught students was actually just by having students work tons of problems until they somehow got it, right? Does this sound similar to anybody? Okay. And the critical thing, though, is even though they understood a lot of the core theoretical results around algebra and geometry, they never had a scaffold that they could build on, right, in order to go beyond this data and calculating with data. Okay, move forward a few 100 years to ancient Greece. The Greeks were not obsessed with data. They were obsessed with models, crazy models, ridiculous models. For the Greeks, the stars were holes in a gigantic colander, right, that sat over the earth. That was between earthlings and the eternal fire, right? And this colander rotated around, and colanders within colanders. This was a ridiculous model, of course, but it was a model that was sufficient to allow someone like Eratosthenes to actually figure out how to use geometry and the fact that if the eternal fire was far enough away that you could actually calculate to a very surprisingly accurate degree the radius of the Earth. Okay, this is something that the Babylonians could never do, right, using curve fitting. And this is really the critical idea of the scientific method, right, that we need to live not only in the real world, the world of data, but also in this world of the imagination or the world of models and theories. And it's really this a cycle, this closed loop between imagination and the real world that really makes the scientific method work and makes science and engineering move forward. And the way you can think of this, and this is pretty simple stuff, but data-driven techniques. Data is very useful for finding an optimum. If you think of navigating through science as navigating a wavy landscape and we're trying to get to the bottoms of hills, data-driven techniques are very good for getting to the bottoms of those hills, but you need some kind of theory or a model in order to jump out, right? When you're stuck, jump out into an entirely new part of the space. Okay, so I'd like to distinguish for this talk two different kinds of problems in signal processing having to do with these cycles of data and models. The first are easy problems. I think we've done a great job over the last 50 to 100 years in solving just about all of the what I'd call easy problems in signal processing. And these are problems where it's easy to develop a model, right, that's accurate, tractable, let's talk about some examples. The Wiener filter. If you have a good model of what signal is, what noise is, if they're actually added together, right, then you can talk about separating them with a simple filter. You can think of match filter detectors for detecting signals using radar or sonar. A beautiful encapsulation of the scientific method in one algorithm is the LMS adaptive filter that actually uses both models and data-driven techniques to optimize in order to for example, do channel equalization over a wire. Where signal processing has had a lot more difficulty with, and Martin kind of alluded to this earlier today, is on what I'd call these wicked hard problems, right? Which happen to be some of the most important problems facing us today. Problems like object recognition, speech recognition, robotic navigation, sensory perception or machine perception type problems. And the key thing that differentiates these kind of problems from the simple problems is the difficulty to model what's going on, right? It's not just like a wire or a cable, right, where everything's linear. These problems tend to be highly nonlinear, incorporating all kinds of nuisance variation. These pictures of Al, if we're going to try to find Al, right, he could have we could have a different camera viewpoint, different kinds of lighting. He could be occluded with a hat. He could have a mustache or not have a mustache. And the critical thing when we try to solve a problem like finding Al in a picture, very importantly, is a lot of these nuisances I've just been talking about, we won't even know them explicitly. They're just implicit in this problem. So it's very, very difficult to model. And it's basically impossible to model using standard linear frameworks. So if you ask, if we're trying to separate pictures of Al from pictures of Don Johnson, where's Don? Don's here in the back. If we're trying to separate pictures, well, linear type methods fail completely. They fail completely because if you take a collection of megapixel pictures of Al, they don't live on anything near a linear subspace. They live on a tortured manifold, right? Nonlinear manifold in this high dimensional space that is intertwined with the manifold of Don Johnson images, right? Which makes it extremely difficult in order to solve this separation problem. And the holy grail of machine perception you can think about is to somehow find methods to simplify this problem, stretch out these manifolds, straighten them so that the Don-Al decision becomes simpler. Essentially what we're trying to do is factor out these nuisance variations, some of which might be known, some of which might not be known. And there's been a lot of progress in the past using all kinds of different features, Fourier methods, wavelet methods, Kepstrom, KSVD, SIFT, right? And all these methods worked to some extent, okay? But then everybody knows what happened, right? The Babylonians took over, right, a few years ago, right? They've been the ones making all the progress, right? Using black box learning, right? Using massive amounts of training data, right? In order to learn high-dimensional parametric systems like deep neural networks. Show of hands, people who know a bit about deep neural networks. Okay, just a little bit, right? So what are these methods? They're actually quite simple when you look at it, and really they're just signal processing. You just take, let's say, an image, for example. You convolve with an adaptive filter. Simple. You then do a thresholding. Very simple scalar nonlinearity. And then you do a pooling, very much like wavelet subsampling. These are all methods that you'd find in Al's book, right? And then you do it many, many, many times. Maybe 10, maybe 100 times you combine this to create some kind of multi-scale structure, not unlike, say, a wavelet transform. And the idea is you put in a picture, okay, of boats in this case, and what you would hope is to get out an indicator function at the other end that somehow peaks up at boats and doesn't peak up at cats, right? So this is a simple primer on deep nets. They're a result of decades of working in the area of artificial neural nets, many times ending up stymieing, moving into dark ages. But in about 2012, the advent of massive training data sets and massive computers to deal with those training sets really set off this Babylonian revolution, right? The singularity is near. I've heard that Al is so convinced that this is coming, that AI is going to take over, that he's thinking seriously about cryogenically freezing his brain. Deep nets are not just going to drive our cars. They're going to cure cancer. They're even going to solve climate change, if you can believe this, right? I think there's a big institute at a school in Lausanne, I think, around deep learning for climate change. Okay, this obsession with black box learning is incredible, right? Is incredible. And one would hope that we can see what the next cycle is going to bring, right? What the next cycle is going to bring. So I'm going to just talk about two brief forays or vignettes into some of the things that we've been thinking about that are potential future directions. The first is thinking about new theory for these Babylonian-type data-driven methods. So can we somehow bring theory into data-driven techniques so that we have a scaffold, Greek-like, that we can understand and extend these methods? And the second is, can we do the opposite? Can we look at our old school model-based techniques and leverage the fact that in a lot of cases, we actually have training data that we can use to make those techniques better? So you can think of these as two sides of a coin. So let's ask some questions. Let's just think about deep learning for a minute and these convolutional neural networks. And let's ask some questions, the open questions. So why are these methods so effective? Nobody really knows. Right? They are, but we don't know why. Can we derive them from first principles? They're effective, but do we know why they fail when they do fail? Because they fail. And can we somehow improve and extend them? And there's a number of groups I'll just mention, working on this idea of theory of deep learning. And I'm just going to talk about our particular approach. Okay? And so now this is going to appeal. Hopefully people will take something, everyone will take something away from this. And hopefully purists will, we're going to go quick. So hopefully there's also something in this for the purists or people working in this area. So this is the spoiler alert. Here's what we're going to do. We're going to take this deep network black box learning approach, and we're going to show, okay, black box deep learning, we're going to show that we can build a model. Right? A probabilistic graphical model. Show of hands, probabilistic graph. Super standard signal processing stuff. Super standard. And what we're going to do is we're going to design a certain model that's going to seem that is very reasonable. Okay? And then what we're going to do is we're going to show that the inference, if you want to do optimal inference under that model, do we know how to do that kind of thing? Sure, we do optimal inference. We're going to show that the calculations from that optimal inference actually correspond exactly to the computations in a deep network. So that means that there actually are models lurking behind some of these Babylonian type systems. And we're going to illustrate, since we've been talking about it, with object recognition. So can we tell the difference between cats, boats, and university presidents? Right? Okay. So simple intro to the idea of this graphical model. I is our image. C is the class. Cat, Martin, or boat, let's say. And G is our nuisance variables, right, which may be known or may be latent. What this graph tells you is that given C and G, you can generate I, right? So on the left, we're generating a picture of a cat. So we set C equal to cat. We set G equal to facing left and happy, because we want a happy cat facing left. And then we generate our image. In this case, one way that you could generate would be get on the phone with Pixar and ask them for a picture of a happy cat facing left. They mail it to you. You add maybe a little bit of noise, and that's your generated image, right? So this is standard graphical modeling ideas. So what we're going to do, and this is now accelerating, we're going to talk not just about this single scale graphical model, but we're going to think about a multi-scale graphical model. Think wavelets, right, or multi-resolution type analysis, where we can exploit the fact that ideas and imagery can be abstracted at different hierarchical layers. So if you look to the far right, this is an expanded graphical model. Looks like the one we just talked about, but now it's multi-scale. And the only thing new here is that everything's labeled according to scale, and we have these intermediate variables z. These z's you can think of as just intermediate scale images, right? These are the these are the think of them as like rendered images or the rendered templates, right? And the way that this very simple model, the way that we're going to go from one set of z's to a set of z's at a finer scale, coarse scales at the top, class comes in, cat, and then we go from a coarser scale to a finer and finer scale. Think like a wavelet synthesis or a pyramidal synthesis. And the way that we're going to go from one scale to the next is simply by a fine transformation, by multiplying by a matrix and then adding a bias. Very simple. So we're going to go from a fine scale image to a coarse scale image by just a simple, fine transformation. So here's a better example. Right in the middle, ZL there. It's an image at a coarse scale. We're going to generate an image at a finer scale by just multiplying by a matrix that we store into this gamma function here. Okay? We do this multiple times. It's just a simple generation model for the final CAD image that is just a product of affine transformations. Does this make sense to everybody? So we're just generating images by multiplying matrices basically together. Okay? So now let's think about inference under this model. Right? So we've defined a model. We can think about inference. The important thing is that this model I just defined is a graphical model. It's essentially a tree graphical model. And we can do Bayesian inference, right? Map type inference. And the way that this inference is going to work is it's basically going to fall out to be message passing, right? Think of max sum, max product, Viterbi type algorithms. Hopefully those keywords make sense, right? So this is completely standard signal processing kind of stuff. We can also learn the parameters of the model, which in this case corresponds to learning the entries in these matrices or these affine transformations. Okay? Theorem, right? Theorem statement. The computations in this max sum inference, if you turn the standard crank, correspond exactly to what goes on in a deep net. Right? Exactly. And so what that means is that deep nets can be endowed with a rigorous probabilistic structure. Okay? So let's just go over this quickly. And I'm going to just use we're just very lucky that the National Science Foundation, there's a new directive out today. I'm not sure if you know this. But project summaries now all have to fit in 140 characters. So you might want to, okay. So we're going to do proof by tweet. Okay? And we're going to go super, super duper fast. Super, super duper fast. So first, if we assume that we're trying to find Al, right, in an image, the very important thing is there's a translational nuisance that we won't know where Al lives within the image. Well, it turns out if you solve the map inference problem under translational nuisance within this model, a match filter just pops out, right? Totally standard, and we get the convolutional layer of our deep net. Next, if you think about the fact that this model, as I currently described it, doesn't handle occlusion, right? If we think of Al holding a book in front of his face, those will actually be cross-faded instead of occluded. And the way to make sure that we have this nonlinear effective occlusion is by adding a sparsity prior that says at any given pixel, only one of these models can be active. If you do that, and again, you turn the crank, you basically have a ReLU layer pop out. Okay, so that's part two. Third, if you think about wavelets, if you think about how you take a picture of Al at a coarse scale and make a picture of Al at the next finer scale, there's some amount of slop that you could move the picture around several pixels, and when you coarsify, get the same image. So that's yet another nuisance. So if you think of this small-scale translational nuisance, maximizing over that, basically max pooling pops right out. So what we see is the three layers types come out directly. Okay? Moreover, if we think back to EM algorithm training, again, totally standard signal processing technique, this corresponds exactly to a specific kind of backpropagation that's used in deep nets. Okay? So, summarize, right? Convolution, thresholding, max pooling, iteration, right? All of these just pop out from calculations of optimum inference. So what can we see? So why is deep learning so effective? right? Well, because there's a generative model behind it that's reasonable. Is it the best generative model? No, it's actually very weak. It's just a product of affine transformations. But it exploits scale in a very real way. We're doing the right thing, optimal message passing, and we're doing EM training. Can we derive methods from first principles? We just did. When does this fail? Well, it fails when deep nets fail when your model is not generated by that kind of very simple, or when your signal image is not generated by a product of affine transformations. Okay, so I got like 1 minute, so let's just talk about the other side of the coin. So that was taking deep nets, trying to look at how we can do foundational theory. Let's look at now at how we can leverage data into standard model-based techniques that we're also familiar with. And let's just talk about solving inverse problems. So inverse recovery problems like MRI, like compressive sensing, where we have a piece of signal of interest X, but we observe measurements Y, right? That are lower dimensional than X. So aliasing occurs, and what we want to, given Y, we want to infer X, right? And of course, there are infinitely many X that when multiplied by A will give you the same Y. So we need to solve some kind of a penalized or regularized inverse problem, right? So the key things, ingredients, are we need to know something about the forward model, right? Meaning the matrix A in this case. And then we need to know something about X, right? What is the structure on X that's going to allow us to solve this inverse problem? And there's two challenges that immediately come up. First is, again, image modeling, wickedly hard. It's a very difficult problem. And second, I won't talk about it later, but the forward modeling also, you can never really know this exactly. So let's just think of your standard favorite image recovery algorithms. Everybody have one in their mind? Okay, 1, 2, 3. Okay, think of your let's just talk about iterative hard thresholding, easiest method. Okay, what do? Right, you're given y equals ax. You want to find x. You start with a guess x0, and then you just iterate. Look at the block diagram. This is one stage of the iteration of this optimization. You have an iterate xn. You basically account for the forward model. You compare to the projection of the measurements into that same space. You get an improved estimate x, and then your x doesn't conform to your signal model anymore, which in this case might be something like k-sparse in some basis. So you perform an operation like thresholding. Okay, is everybody with me? I'll finish in 1 minute. Yeah. So let's just take this one iteration of think of your favorite iterative algorithm, and just think of taking that one iteration now, and instead of looping back on it, think of it as a block in a network. Right? So xn comes in, and xn plus 1 comes out the other end. So now we can think of it, we can think of any iterative algorithm as actually a set of blocks connected, unrolled basically. And it's completely equivalent. The calculations are equivalent. The answer is equivalent. Okay, but what this network kind of thinking can be useful, right? Because now we might imagine changing or augmenting either the forward model, or our projection onto our model class, right? There's HK in this case, right? With more flexible methods. So let's just talk about a quick example of taking out wavelet hard thresholding and putting in some kind of deep net like denoiser. Okay? Moreover, we can get training data. Who doesn't own an MRI machine and also have a ton of MRI data, right? Okay? And so given training data, a collection of XTs and YTs, what we can do is we can take this iterative algorithm that's been unrolled, and we can put in the Ys, the measurements, see what comes out the other end. That's that XNT. It should be equal to XT, but it isn't. So there's an error, and that error can be used backpropagation-like to tune the parameters of this optimization. So you can think of it as bringing together the best of these sort of black box methods and optimization type methods. And it works really well. Like, it's crazy. So far left is kind of standard recovery method. Middle is state-of-the-art recovery method for compressive sensing today, this BM3D amp. On the right is this learn network approach, right, where we use a bunch of training data to optimize. It's about 17 times faster, well, not 70, 70 times faster than AMP. and considerably better performance, right? So there's a lot, I think there's a lot of legs in this space. So I will end because I'm over time. So these are early days. I found this picture randomly on the internet. These are early days for incorporating models and data in signal processing, in particular to solve these wickedly hard problems. I think we're going to see talks through the rest of the afternoon. I think you could think of signal processing today. I think a place that fits into this data science world is really about sensor data science, if you will. I think it's also clear that we start to move from these linear type methods to more nonlinear methods. And we can actually think back to Al's PhD thesis, right, and the homomorphic type methods. I probably don't have time, but I'll just mention that we need to be patient. Right? We need to be very patient in this as signal processing people. It took 1,000+ years to replace an Earth-centered universe with a sun-centered universe. Okay? And one of the reasons it was so difficult is predictions using the Earth-centered universe were no better, or a sun-centered universe were no better than with the Earth-centered universe. Right? Copernicus was not more accurate. Actually took another couple hundred years for Kepler and then people who cleaned up Kepler to actually find a method that was both more attractive in theory and also better as far as fit with the data. So I'm really excited. I think we should be in this for the long haul. And again, happy birthday.